This begins EE 555 discussion on Wednesday, April 2nd, 2014.
Okay, good morning everybody. Today we'll talk a little bit about some flooding algorithm, and then we'll see some mobility problems. Okay, so first of all, have you seen anything about reverse path forwarding in class? You saw it? Right, good. So if you remember, this is an algorithm that does what? It controls flooding, right? So it tries to avoid excessive flooding. What architecture? Like a node will not forward a packet if it doesn't belong. Link, it's not coming, like the packet's not coming from a link that belongs to the shortest path to the source of the packet, right? Use that concept over here to analyze the problem. And let's see. Consider the operation forwarding algorithm in figure 1. Using the same type of paths from all nodes to the source node A, and indicate these paths in a graph using thicker shaded lines as in figure 1. That if these paths were the least cost paths, then node B would receive a copy of A's broadcast message from node and D under RPF. Okay, this is the source on B, and we want to draw a graph like this in order to indicate that to draw a graph that represents what? A cost path. Sorry, so this is a known shortest path link. You see? This is a line. That's what we want to draw over here. So, paths and graph from all nodes to the right? So we want to support path structure over here that gives this outcome when we apply RPF, which means that B is from A, from C, and from D. A, C, and D. Clear what we're trying to find? Any ideas? Basically, we know how RPF works. Now we'll apply RPF and say the other way around. There might be many solutions. That's fine. We're just picking one. And we can think if, you know, like what else can happen. So if RPF packet from A to B through A, what does this mean? The shortest path from A to A passes from A, first of all. Do you agree? Because see a packet from itself, let's think about this dummy case. So A will forward the packet to all except the source, okay, if it belongs to the shortest path. So A will forward. Clear? What about A to C? A, but how C will react? We want C to forward the packet to the destination, not to the, right, to broadcast the packet to B. What does this mean? Do we need C link CB to B path? No, exactly. Why is that? We just care where the packet is coming from. No? So this link over here, in order to forward the packet using RPF, this a minimum cost path. Do you agree? This link here. So C will forward the packet if this link is the minimum cost link connecting. Agree? Okay. Now let's see the same. We'll draw the diagram, but let's see the case of D. We want D to deliver packet to B. What can give such a case? Applying RPF. D to B. We want, of course, this is isolated. It should come from here. Right? This means that this link belongs to the shortest path going to A. Agree? About this, because if this is the case, then we don't forward back to B. So the packet needs to be coming from this side. In order, like in this case, if D receives a packet and this link is short going to A, then D will forward to B and G. Do you agree? Back here, what can happen over here? We can have the packet will be received by whom? C will forward the packet to everybody. If this link is not the shortest path, then E will ignore it. But if this is the shortest path, this guy will forward it to E. And if this is the shortest path, then E will forward to D. And so we can draw a path that goes like this. AC, CF, FE, ED, because we want to reach also D. And then that covers all the cases. It traverses the, right? Do you agree? Any questions? You don't agree? Tell me, guys. So the tricky part here is find a set of paths from all nodes to the source A. Where is the parenthesis closing over here? And indicate the paths in the graph using thicker shaded lines as figure 1, such that if these paths were the least cost path, then node B would be of A's broadcast message from nodes A, C, and D. So I'm telling you, not to think like, oh, if I want to receive a message at B from C, this doesn't need to be the least cost path. Because the algorithm operates, we say C will forward the packet if the packet is coming from the least cost path. Okay. So with that said, let's draw the diagram in this case. Okay, so I'm using thicker lines to indicate the shortest path that gives this kind of behavior. And you can think at home of other cases that the same can happen, okay? The graph is small, so we shouldn't have many cases, but now if we want to follow the graph structure over here, with an arrow, the packet will be forward, and we represent with a packet, an arrow and a small square over here, packet not forward routed. Why? Because according to RPF, it's not coming from a minimum cost path, it will not be forward. So in this scenario over here, which arrows will be with a dash, with a small square? Any ideas? For example, if a packet comes from here, C will forward the packet to B. Is it going to be forwarded somewhere else? This path? No, right? Because it's not, this is not a minimum cost path. Is this a minimum? No, according to our assumption, it's not. So the same will happen over here. Okay? You agree? Okay. The algorithm is simple. It's just that, we need to think like carefully how it evolves. Yes. Now let's also draw these cases over here. Okay. Now if you don't have questions, let's see another problem.
The time is 11.
Which is related to mobility. One proposed solution that allowed mobile users to maintain their IP address among foreign networks was to have a foreign network advertise a highly specific route to the mobile user infrastructure to propagate this information throughout the network. Okay, you saw that in class. Scalability as one concern. Suppose that user moves from one network to another. The new foreign network advertises a specific address to the mobile user. The old foreign network withdraws its route. Okay? So it kind of refreshes the new route to the old position. Consider how routing information propagates in a algorithm, particularly for the case of inter-domain routing among networks that span the globe. In which case we have, big networks that are far apart. So the problem is in the worst case that can happen, right? Will other route diagrams immediately to the new foreign network as soon as the foreign network begins advertising this route? That's a fact. Think about it. So we have the case of a foreign network advertise a highly specific route to the mobile user, use the existing infrastructure to propagate this information throughout the network. Okay? Suppose when a mobile user from one network to the other, the new advertises a specific address to the mobile user and the old foreign network withdraws its route. Consider how routing information propagates in a distance vector fashion. So the question is, will other routers be able to route datagrams immediately to the new foreign network as soon as the foreign network begins advertising? What do you think, guys? Vector algorithm, as it's given over here. Right. This is the right answer. The problem is that distance vector is distributed, right? It's not a centralized controller that says, okay, not over here, or the guy is over there. So until the algorithm converges, and in some previous lectures, like it takes some time, or log something, I don't remember the number. As happens, we won't be able to access, right? The information needs to propagate. So let's just sketch an answer over here. So the answer is no. All the routers might not be able to data. And the main problem is that this is because the distance vector algorithm, as well as protocols like PGP, which is used for intra-domain routing, like in our case, the algorithm is decentralized and it takes some time or converge. Okay, so the problem is when the algorithm is running before it terminates. All right, so are you done with that? Is it possible for different routers to believe that different foreign networks contain mobile users? Different routers believe that different foreign networks contain mobile users. Happen. No, but this it doesn't belong to foreign networks, right? It belongs to one network, but it's seen from two different routers. That's what we say, right? So we want to think of a case that it's like somebody in New York. When this can happen? You didn't update your friends fast enough that you moved, right? So your friends in New York, they see you there. Your old friends here, they think you are still here, but you are not. The problem is that you didn't update them fast enough. So that's a scenario that this can happen. Make sense? So those are tricky questions like involving mobility to better understand all the details about mobility. As you see, it's very clear all the time. Okay. So the answer is yes, this can happen. It can happen one of the nodes has just left a foreign network and joined a new network. In such a case, the routing entries work. And this is a foreign network. Might not have been complete. When the new network are being propagated. Okay, that's a scenario that this can happen, but of course it's going to last for a very small amount of time. Many bad things can happen during mobility, of course. So the third question is, discuss the time scale over which other routers in the network will eventually learn to the mobile user. What's like, do we see any time it takes for this to propagate? How long it can be? It's a simple question, just think about it. Like, is the same, can it is the same to move to Asia or somewhere? Obviously. So there is a dependency between what? The number of hosts. Between what? Between the edge router in the new network. So there is time it takes a path to the mobile node depends on the number of between the router, a given router, and the edge router of the foreign network for the node, where it's going to. Okay. Is that clear? Scenario. Now let's see another problem that is slightly more complicated. So suppose the correspondent in figure 2.1, I'll give you this that has everything over here. Right. Suppose the correspondent in figure 2.1, this one, mobile. You remember the correspondent is what? The node that talks, right? Now we assume that we have a mobile to mobile scenario. So suppose here is mobile. Sketch the additional network layer infrastructure that will route the datagram from the original mobile user to the now mobile correspondent. So the structure of the datagrams between the original and the now mobile correspondent as in figure 2.2. So let's see over here what we have. We have the permanent address of the mobile node. It's connected through a WAN. We have the foreign agent here. The home agent is here. The visit network is this one, and this over here. What is the care of address? Right. Is it here? It's kind of tricky, but yeah. Address might be also the address of this of the router, right? The network part of the address. So you can just send it to foreign agent. Basically, I'm talking about the foreign agent, and the foreign agent can direct them to the mobile node, right? In a similar fashion as in NAT mapping. Okay, so we understand the simple case. Now what happens in the case where we have mobile to mobile means that, no, let's see also over here what's happening. We want to send the packet, the correspondent send the packet to the mobile node. Where it's gonna send the packets to, the datagrams? To the home agent. What is the destination address? The permanent IP. So we assume that the permanent IP is exchanged. We can reach, when we want to reach somebody, we get his public IP, his permanent IP. We destinate the packet to the permanent IP. And this will hit the home network, right? The home agent. The agent takes care of what? Encapsulating, building a tunnel from the to the foreign, assuming that they have exchanged information, they have reached each other, and they know where the new mobile is, right? So in this case, we make the whole process agnostic, but the correspondent can still reach the mobile node, which we want. You remember the triangular case, like we go through the home network. Okay, so now we have encapsulation over here. We encapsulate the old datagram to the destination. Now is the destination of the care of address or of this guy. Make sense? And in such a case, is received over here. It's being decapsulated. We remove the header, and now the foreign agent, what? It can forward the packet to the mobile node because it has the of his own permanent address. Okay, but what happens if, let's go back to the question. Show the structure of the datagrams, no, that's later. Network layer infrastructure that would be needed to route the datagram from the original mobile user to the now mobile correspondent. We know from here how to reach this guy. What happens if this guy wants to reach the correspondent? So that's what we need to draw in addition to what we have. Thanks. Did you see when I was presenting, did you see this graph ever? Or it's the first time it goes up? Okay. So now, okay, we have this communication and then the encapsulation, decapsulation, we're done. And we said that we want the foreign, the mobile reach the correspondent, which is mobile. Now, instead of drawing this, please forgive me that I'll give you an already nicely designed graph. I'm not going to draw it for you. It's going to take, I'm going to show you this. So, see what happens in this case. That's the answer to the question, guys. So, the answer, first of all, before I show you and analyze what we will do, can you see what happens in the scenario when this guy wants to communicate to the student? How would you imagine the structure? Triangular, okay. So isn't it the same as the case where we have just correspondent and want to reach another mobile station? So it's completely symmetric, right? So a mirror of the initial system, like the mobile node in the foreign network needs to hit the home agent mobile correspondent, right? And the home agent of the mobile correspondent to the foreign agent of the correspondent, and then he can reach. So that's what we do. This part, it goes like this, okay? I think here you can see everything. So the correspondent, we said that it's mobile, so foreign agent of this guy, because we assume he already moved somewhere, it's mobile, right? He wants to talk to this node. He will use his permanent address, shown here with a typo. Okay, the home agent will make a tunnel and encapsulate. It sends the packet to the foreign agent care of address over here. Do you see the gray? You see the destination here? The permanent address is characterizing this mobile node in the foreign network, that's clear. And then what else do we have? Here we represent the source address. It is also sent, right? So in any case, assume that. Now if the mobile node wants to talk back to the other guy, to happening. He talks to his home agent, the permanent being used, assume it's 10.10.10.1, and then the home agent will encapsulate, it's going to reach the care of address in the new network. That's all. Do you agree? I guess with this example we understood, everybody understood the structure of, That's all. So I'm going to attach this in the solutions. Now, let's go to problem number 4. In mobile IP, what effects will to end-to-end delays of datagrams between the source and the destination? Actually, before that, we might want to do some writing for the previous problem. Do you want me to write down some wording for the solution, or you got the idea? It depends on you. Okay? Sorry for that. Let's go back. Let's just verify what we just said over here, because I don't want to attach only one picture. And let's do the whole thing over here, since we have time. So the question over here. So the structure of the datagram. The structure of the datagram is shown here, but let's see. if the correspondent is mobile, any datagrams destined to the correspondent would have to pass through the correspondent's home. The foreign agent in the net being visited would also need to be involved. Since we're talking about foreign agent to home agent of the mobile correspondent. See, it is this foreign agent that notifies the correspondent's home agent of the location of the correspondent. Alright? And also datagrams received by the correspondent's home agent would need to be encapsulated and then decapsulated between the correspondence home agent Okay, that's all we know. We want just to document what we just said, okay? Continue to the next problem, guys. Alright, so now, in mobile IP, what effect will mobility delay of the datagrams between the source and the destination? Why? Okay, that's right. We have delay, and also what kind of delays do we have? More hops. Usually you can't click more delay, but yes, it can happen, right? But what kind of other delay to have? What other processing we do in the packets? We just talked about it, right? And cap decap, right? So that kind of imposes some overhead too. The tunneling. So that's the answer. So let's write this down. So let's, because datagrams must be fed to the home agent here to the mobile, the delays will generally be than we had, right? You saw that case in class. So, however, as we said that this might not happen, that in some particular scenario, here we say generally. This generally might mean, and you cannot guarantee that the triangular inequality will hold in this case, because we're talking about might be just a shorter link, right? Or that the sum of the two is less than the direct. It might be, right? When this can happen. I mean, in general, you can, okay, this will never happen, but this is just, an exception case, exceptional. Yeah. Of course, there is certain things that take place, so we need to account also for that. And also, let's note that indirect routing which is what also adds agent processing delay, e.g. and cap. Okay? And let's go to the last problem. Problem number 5. Consider two mobile nodes in the foreign network having a foreign agent. Two mobile nodes. If two mobile nodes to use the same care-of address in mobile IP, explain your answer. If they have, how? If they don't have, how they can be reached? Think about that. Let's see this example over here. Oh, it's here. Care-of address. So we are talking about over here, and they both use the same care-of address. Is that possible? You say it is. Any other opinions? No. And why it's not possible? We're talking about the same IP. Okay, yeah.
So if we have got two different home IP addresses, say belonging to the same network or to the different network, it would be an ambiguous situation for the router to direct the packets.
For which router? Over here?
Yeah.
How would this perform in the case of NAT? If that was a NAT interface, what happens? This guy uses one public IP to the left of the network, and internally he has its own mapping, right? So it's possible.
5 minutes left. Just
Thank
a
you.
heads up, yeah.
And the reason for being possible is that the care-of address is the permanent. So each mobile will have its own permanent address. So this guy over here, one mapping. Why he can build one-to-one mapping? Because that's the difference. Over here, In NAT, we have port numbers. So port and IP mapped in a unique fashion to an internal IP. Do you agree with that? Over here, we saw this guy, when he receives a packet, the first thing is for encapsulated packet to reach the router. So two mobile nodes use the same QoS address, the encapsulated packet, decapsulate the packet, and then can reach internally, right? Because they have different permanent address. That's how it works. Okay, so let's two mobile could certainly have the same QoS address in the same visited. That's important, eh? In the same, they should be in the same network. In the same visited network. If the QoS address is the address of the foreign agent, which I told you this is the case, like we have the address of the router being the destination in this case, then this address would be the same between two different mobiles. And then once the foreign agent decapsulates the tunneled datagram and determines the of the mobile, then separate addresses would need to be used to send the datagrams separately to their different destinations within network.
Out of time.
Thank you. And as we said, this is what is used internally, okay? That's it. Do you have questions on that? All right. Thank you very much.
This concludes EE 555 discussion on Wednesday, April 2nd.